coding theoretic problems. So in fact, my plan is to sort of introduce kind of, one of these coding theoretic challenges that arises when you want to design very, very efficient proofs, especially if you care about, running these things in practice. So I'm going to start off by giving a very sort of, hand-wavy sketch of the sort of cryptographic setting. My apologies to any of the cryptographers in the audience if I say anything that's too blatantly false, but I'm just going to try to give you a sense as to how, codes with very nice properties can be useful. And if I time things well, then eventually I'll be able to go into more detail on the specific codes that we use. Okay, so actually I'm quite lucky because some of this cryptographic context was already introduced in our previous talk. So I'll first sort of quickly remind you of interactive oracle proofs and also then interactive oracle proofs of proximity. So what are these things? Briefly, I like to think of them as sort of an interactive version of a PCP. So here we have our prover, and we give it the prover both like an instant X and a witness for that instance. So you can think of there's some sort of underlying NP language. Choose your favorite NP language like satisfiability. So the prover has the instance and also say a satisfying assignment, and the verifier is just given the instance and wants to decide if X is in the language. And now a classical PCP, as we've seen, what would happen here is the prover would send a proof to the verifier, and then the verifier would toss some coins, and based on these coins, it might read a few locations from the proof. If this were a PCP, we'd be done, but in an IOP, we allow some interaction. So now the verifier can actually decide, hey, I'm going to challenge you again. So this is sort of like what Shubhangi said. And then maybe based on this, the prover will have to send a new proof. The verifier might toss some more coins, read a few more bits of the proof, challenge, so on and so forth. This could repeat for a large number of rounds. And in the end, the verifier decides if he wants to accept the input or reject, right? Okay, and so sort of in order for this to be efficient, the important parameter from the verifier side is that we'd like the number of queries to be much shorter than the witness length, right? So for a PCP, we often talk about like a constant number of queries. Here I'll be interested in more like polylogarithmic, but the details for the verifier are not too important. Actually, I'm going to point out a different sort of efficiency metric, which perhaps you're not very used to thinking about. Usually we think of the prover as being some sort of all-powerful being that can usually denote him as Merlin, and he can do whatever he wants. And then, poor verifier is the only one who's computationally bounded. But of course, in practice, if I actually want to run a proof system, well, it'd be useful for the prover to also be efficient, right? So we're going to be looking for proof systems where the prover can, come up with the, proofs pi1 up to pi2, so on and so forth, very efficiently. Okay, and now I'm not going to go into the cryptographic details of, how you convert such an interactive oracle proof to like, a proof you could use in the blockchain. But trust me, this is how, a lot of these sort of snarks or starks or snargs, all these funny named things are actually constructed in practice. Good. So, okay, so actually just like in the, the setting of Frye, we're actually more interested in so-called IOPs of proximity. So this is sort of a slightly weaker guarantee where, maybe the prover, you can imagine him as sending the input to the verifier. And now the verifier just wants to decide if the input is somehow close to the language, or we're only going to require the verifier to reject if the input X is far from being in the language. So the previous example was a classic example where, say, X could be the set of all Reed-Solomon code words. Or sorry, L could be the set of all Reed-Solomon code words. And so yeah, the setting now is the verifier will read the entire input, only make some queries to it. And again, we interact just as before. And at the end, the verifier will make this decision. Is this clear so far? Good, so this is kind of the setting. And now we're going to sort of focus on a specific kind of IOP, which is actually IOPP, I should say, which is very similar to the IOPP for Frye, which the language just consists of all code words. But I'm also going to add an additional constraint that the message should maybe satisfy some predicate. Okay, and here, this is where I'm starting to really sweep things under the rug, exactly what this predicate is. I'm happy to talk about it offline if you're interested in the details. But for now, just think about it as some sort of efficiently verifiable statement about the message. And importantly, this is sort of public. So both the prover and the verifier know this gamma. Good. And so, pardon me?
Doesn't make sense.
Hmm? Yeah, I'm saying C of M. Sorry, this is my notation for like the encoding of the message. So this is another way of saying this is just all code words whose underlying message happen to satisfy a certain property. So it's a specific subset of the entire code. Good. Thanks. Yeah, of course, stop me if anything is unclear. Good. But yeah, so this is then the setting, and then of course, they'll interact back and forth for a while, and afterwards, the verifier should decide if C is close to being a code word, and moreover, is close to being a code word whose underlying message satisfies this gamma. Okay, and what I kind of like to say is that This is again, I'm putting standard in quotation marks because there are some details here, but it's not too difficult to get prover time, say, order k log k. And I should already say here, this is already beating what we can say do for PCPs, right? Because for a PCP, there's been a lot of work getting like, order n polylog n, or I guess order k polylog k, because my witness size is say k here. But we can have like, just a very simple logarithmic dependence on k. So very close to linear. And then the prover time, say, is I guess log squared k, just to be safe. But if I'm being greedy here, I would like the prover time to be properly linear in the witness size, right? So it's just, the amount of information that it has to read to even run this protocol is the order of how much time it takes to actually run the protocol. Yeah, let's think of gamma as being, yeah. So it'll be like a very efficient thing, sure. Good. So how can we try to come up with, sort of saying that we have an IOPP with roughly this complexity, how can we get an IOPP where the prover time, we shave off this factor that's logarithmic in k? Okay, so this is where the first sort of coding theoretic idea comes into the picture, which is to use interleaved codes. Okay, so say we have a code with some distance delta, and here's my notation. So I'm going to be using relative distance, but actually later it'd be nice for me to use weight as kind of the absolute number of non-zero entries. So apologize for that, but so that's how I'll be denoting it. So we have a code with given relative distance delta and some integer t, which will be the interleaving parameter. And so from any code C, I can construct this interleave code in a very sort of simple way. I take my messages, I view my messages being, say, a t by k matrix. So I could write it as, a t by, so I have t messages, m1 up to mt, and then I guess encode them one by one. And this gives me a code word. Typically, for an interleaved code, I should maybe point out that you view the block length as n and the alphabet as being f to the t after this step. That's not too important for well, it's kind of implicit in what I'm doing, but those details aren't too important. You can just think of it as a way to encode matrices into matrices, just doing it row by row. Okay. And the basic idea is to say, okay, suppose I have an interactive oracle proof of proximity for the sort of language I described on the previous slide. Then I'll get an IOPP for this interleaved code, and we'll show that this new IOPP for the interleaved code has the linear time, prover time that we were looking for. Okay, and of course there's something a little subtle going on with how like the precise gamma changes, but again, I'm ignoring those details. Okay. Good, so how does this go? So again, we have our prover and our verifier, and the first message would say be like this supposedly interleaved code word, and the the prover is holding on to this t by k matrix whose rows are m1 up to mt. So the underlying message corresponding to this interleaved code word. Okay, and then maybe there'll be some communication, but at a certain point, the verifier will say, okay, I'm happy that I'm happy at least to start off, sort of reducing the size of this instance to a smaller instance size. So how does this go? He starts off by sampling sort of a random vector of length t. So this is just a uniformly random vector, and sends it to the prover. And now the idea is the prover and the verifier are going to say, consider this new code word, which is the linear combination of C1 up to CT, determined by this, this random vector R that the verifier came up with. So this is kind of like the challenge in, an IOPP. This is sort of the verifier is challenging him. Okay, prover, please switch to this new code word. And also, since C, I'm assuming, is a linear code, this is actually the encoding of the message, which is also the same linear combination of M1 up to MG. Right? And then, okay, so the prover says, okay, here's this code word you asked for. This is sort of similar maybe to actually the step that we saw in FRI, where it was kind of, we folded the polynomial. It's a bit similar in spirit, maybe. So this is the new code word. First, the verifier probably wants to convince himself that, okay, did you actually construct this properly? So all he does is say, he reads, say, some number of bits from C0, and say if it reads like this ith coordinate here, we'll read the ith column of the original matrix C and verify that if, if he does R1 times, C1 at coordinate I plus R2 times C2 at coordinate I, RT plus CT at coordinate I, he does indeed get the appropriate coordinate of C0. So, he just does that often enough based on the minimum distance of the code. And once he's convinced, the verifier and the prover will say, okay, let's now run this IOPP on this new instance that we assumed existed. Okay, so it's just sort of a way to kind of collapse the instance size by this factor T. Any questions? Pardon me? Yeah, exactly. So I'm really hiding all the details with what this gamma is and how to do this. There's actually a lot of subtlety involved in making sure this interleaving and collapsing is consistent with the appropriate gamma, but yeah. I'm happy to talk about it offline if you're interested. Okay, so how does this actually help improve over time? So again, let's recall this interleaving parameter I'm choosing to be like order log n or order log k. We're going to choose constant rate codes, so k and n are comparable, so it's not too important. And let's say like the witness size originally had size capital N. I can rewrite this as a k by t matrix, right? As long as k is n divided by t. And then so the first step for the prover, of course, is to encode M1 up to MT. And let's suppose that I have designed a code such that encoding a message of length k takes order k time. Okay, we have such codes. I'll talk about one very nice one in the second half of this talk. Then how much time does it take to encode this interleaving? Well, I need to do this t times order k, and by my setting, that's exactly order n. So that step has the right sort of complexity. The next step as well is, of course, we still have to run this IOPP on an instance now that has length k, right? But well, on this instance, I said we have complexity order k log k, and since k was n divided by t, this is order n again. Okay, so we get the linear time prover that we were looking for. Is this clear? Okay, so there's a catch here, of course. Unfortunately, in going from the matrix C to like this code word C naught, we could have cheated. But fortunately, we just had an entire talk about the answer to this question. So let's imagine that C initially was far from this CT, but then So imagine that the original matrix was far from the interleaving of C, but then based on the randomness the verifier chose, the prover got really lucky and suddenly it was, this C naught you asked me to generate is now actually close to the code C, so I can just honestly, continue and convince you that, I had a genuine, the instance should have been accepted in the first place. But we sort of know the answer, we can use proximity gaps to say this is very unlikely to happen, okay? So yeah, with high probability, this new code word that will be generated in response to the verifier challenge of, R1 up to RT is also very likely to be far from the code. Good, so I actually didn't really know how to draw this well, so I think actually Shubhangi's picture was way better than mine, but this is my picture. So essentially, if you imagine you have a code with like some certain minimum distance here, and you imagine you take another affine space, this is, I'm going to state it in sort of the contrapositive way that Shubhangi stated. So I'm going to say, as long as at least one point from my affine space is far from C, then actually almost all of them are far. So almost all of them are far from the code C. Okay, and so you should think of, in our context, we'll take U to be the span of like the rows. If the matrix is far from the interleaving, then at least one of the rows is far. So, and we have that almost all of the choices for C naught would be far as well. Okay, and yeah, actually, I don't even think I really need this slide because we already talked a bit about this. Maybe the one point I really want to point, one thing I really want to point out here maybe is that first of all, we need a statement that works for arbitrary codes, whereas Shubhangi was just talking about Reed-Solomon codes. So that means that, okay, what she called delta, I'm calling tau now. But for example, we can only work up to say like a third of the minimum distance using sort of a generic result. And here also we need the field size to be very large in order for this probability that, the prover gets lucky to be small. So for soundness, we need a large field size. Actually, like very recently, I only learned about this 2 weeks ago, some work by, I think it's Gao, Khan, and Li have an improvement to sort of increase this, this value of tau, but I haven't looked into exactly what that implies for us. Okay, good. How am I doing on time, by the way? Cool, good. So I guess I'm about halfway done the talk. So the summary of everything we've seen so far is that the prover time will just be dominated by how long does it take to do all of these encodings according to whatever code C I choose. And this is where I get the freedom as a coding theorist to come in and say, okay, let's just pick a code that has very fast encoding. The other, of course, requirement was that we need good distance in order for this proximity gap to result to apply for us. Okay. So what codes should we use? This has sort of become my new favorite class of codes. They're called repeat, accumulate, accumulate codes. And these were first introduced in the late 90s. There was some work on them as well in the mid 2000s. And I think cryptographers have sort of recently discovered them and have started trying to plug them into different settings, including the setting I've just shown today. Okay, so what are these codes? The sort of the main protagonist is what I'll call like the accumulator matrix. And I don't know why, but in recent years, I've been writing matrix vector multiplications with the vector on the left, so bear with me. So it's like a row vector multiplied by a matrix. So if x times a is equal to y, what happens? So basically, y1 will just be, I copy down what was in the first coordinate of x. Y2 will be, okay, one way to say it is I copy the previous value of y and then add in x2, or by induction, that's x1 plus x2. Similarly, you know, y3 would be y2 plus x3, or x1 plus x2 plus x3, or generally it's just like a prefix sum mod 2. That's all it is. It's a very simple sort of operation, okay? And if you recall, like maybe your basics algorithms course, like prefix sum, that's one of the fastest things to compute, even forgetting mod 2. You can do, like, first of all, I only need to do n minus 1 XORs, just by the way I described it, right? To compute any coordinate yi, I just need to do yi minus 1 plus xi. So sequentially, it's super fast. Even in parallel, they're nice, you know, parallel, low-depth implementations. So concretely, this is one of the fastest matrix vector multiplication vectors you're going to find. And yeah, here's the vector, the matrix which implements it. Okay, it's just got ones on and above the main diagonal. Good. Is this clear so far? So then what is an RAA code? I'm going to stick to the rate 1/4 case. And also, so for most of what I'm going to say from now, I'm going to be working over F2. Recall for the proximity gaps, I wanted large fields. So this will be kind of an issue to deal with at the end. But for now, let's just imagine we're working over a binary field. The RAA coding is very simple. So I start with my message, which has length k. And the first thing is to repeat. So that's the first R. So repeat, accumulate, accumulate. So first I repeat. I just write down my message 4 times. So this way I've already got sort of a rate 1/4 encoding, right? My redundancy is, you know, 3/4 times, yeah. I have a code word of length 4k from a message of length k. But of course, this is a terrible code, right? I mean, if M had only a single one, then okay, its encoding has weight 4. So I've barely gained anything. But then we start to add in some, you know, non-trivial steps. So the first thing is to permute the coordinates. So, you know, maybe I'll copy this coordinate here all the way down there and, you know, just sort of scramble the coordinates in some way. And then I run this accumulation step. So I do this prefix sum mod 2. Good. So this already would give me what's called an RA code, a repeat accumulate code. But I wanted to repeat accumulate code, so I just do this one more time. So I permute one more time, and then I accumulate one more time. Good. Okay, so if you prefer matrices, here's a way to view the generator matrix. You know, this repeat step is just implemented by a matrix which has, let's say, 4 ones per row and one per column. And then a permutation matrix, of course, is just any matrix that has exactly one per row and column, right? And the rest of the entries are 0. Then I have this accumulator matrix, which was, you know, ones on and above the main diagonal. And then I have one more round of this. Yeah, so they're going to be chosen randomly. But for now, they could be any permutations, yeah. Good. So first of all, you might ask, why did I do these 2 rounds? Why not just 1 round? So you could, in principle, define like what's called an RA code like this. So you just repeat, permute, and then accumulate. But unfortunately, you'll never be able to have an asymptotically good code this way. So if you want, say, like, you know, repetition factor, which is a constant, your minimum distance will be upper bounded by something which goes to zeros and goes to infinity. It's just they're a bit too simple in order to get constant distance, but already with 2 rounds, you can get very good distance. Okay, and before I actually, you know, say anything too formal, I'm going to give an analogy. This is from my co-author, Ron Rothblum. Like any good analogy, if you think about it too much, it stops making sense, but I think it's still kind of useful as maybe a bit of a sense of how this goes. So, you know, if I start by just repeating, you know, I have like my rocket ship, which is trying to, you know, get up to a good distance. And okay, at this point, all I have is like distance 4 over n, because, you know, weight 1 vector only is going to have weight 4, so its minimum distance is 4 over n. But then you do kind of the first stage where you do round 1, and okay, your first stage rocket blasts you up to a distance like roughly 1 over square root n. Okay? And of course, that's not quite where we want to go, but then, you know, your second stage kicks in, and then you're actually, you know, in outer space, and you have proper distance 0.19. Okay? Good, so this is actually what we can show. If you choose your permutations randomly, with high probability, you'll have a minimum distance about 0.19. And just for context, you know, you can't really hope for much better than this. This is the Gilbert-Varlamov bound for rate 1/4. Okay. So this is the statement. Let me give you a bit of a sense of how we would prove this. Oh yeah, I should really mention that, you know, sort of our work was really to try to get some very concrete bounds on the failure probability, which is kind of important for these cryptographic applications, like how large does n actually have to be so that I can really say with like probably 2 to the minus 20, you're going to be okay. But we used a lot of ideas that had appeared in prior works. And all of these works usually use what they call this IOWEF, or input-output weight enumerator function, which is a very complicated way of like stating the following count. So for given like integers a and b, I can ask, okay, how many vectors are there of weight a such that after I accumulate them, I'll get weight B. Okay? So it's, A could be 5 and B could be 20. How many vectors of weight 5 have accumulated vectors of weight 20? And now I would challenge you, pick any old matrix A. This is probably going to be a very difficult thing for you to compute. Like it's, especially a binary matrix, it's not really clear that this can be done. But actually for this accumulator matrix, it turns out there's a nice formula. Don't worry too much about what the formula is. Just note that, okay, it's a couple binomial coefficients, you can work with it. It's kind of, it's not too bad. Okay, and in particular, I can define the following probability. So if I randomly sample a vector of weight A, what's the probability I get weight B after accumulating? And I'll just denote this by P sub A to B. Okay. Good, so then if I were trying to analyze, say, a random RAA code, let's say I start off with a message and it has weight W0, my first step. Then, I might repeat this, and then I get weight 4 W0. And then, you could imagine this is kind of like an adversary trying to choose the worst possible message for you. But, over the randomness of this permutation matrix, I can then pretend that, okay, it doesn't matter what you gave me at the start. I now have just a uniformly random vector of weight 4 W0. So then when I plug it into this accumulator matrix, I can say something about the distribution of the output weight. I recall this was what this notation represented. Right, so now I know, okay, with some probability I've moved to weight W1. I randomly permute again. I get a random vector of weight W1. And then, with some probability, I'll move to weight W2. Okay, so this is sort of how the analysis goes. So how much more time do I have, actually? 6 plus delta. Okay, yeah, and I think I can say some more details then. So to say a bit more about the analysis, what do you do? This is kind of, if you've seen like the proof of the Gilbert-Varlamov bound or something like that, I mean, what do you usually do? You introduce a random variable, which is counting the number of non-zero code words, say of weight at most D, where, I'm shooting for, distance delta. So delta times n is the maximum weight I'm going to allow. And the probability that my code will have, bad distance is equal to the probability that there's at least one non-zero code word which has large weight. And then you apply Markov's inequality to this, right? So, the probability x is at least 1 is at most the expectation of x. Okay? So then it's just a question of what is this expectation? And, okay, it's got this kind of crazy expression, but it's really not that difficult. All it's saying is, okay, so I count how many ways I could choose the first message weight, how many, intermediate weights could I get to, and then how many final code word weights could I have? And then this first binomial coefficient is just saying, okay, well, how many messages did I have in the first place that had weight W0? And then I have my probability of moving from that, okay, after repeating it to weight W1, and the probability of moving from weight W1 to W2. So I just kind of sum over all the possible trajectories of weights that my messages could take, and I sum over all the possible messages. Okay, so this is the expectation. How do you want to analyze this? This is actually kind of also implicit in this work, this kind of idea. You sort of break up the sum based on W1. So this is actually where kind of in, the analogy I gave earlier is actually not such a big lie. You sort of you imagine what happens if you have a bad first stage. So what if after the first stage, I didn't get very good distance at all? And you could even say log squared n. And you can show, this is fairly unlikely, and your final bound will be something like inverse polynomial. But so long as your first stage is reasonably good, using some sort of different inequalities, this becomes a bit more like sort of a calculus problem in this case, you'll get a bound that kind of looks like it's actually very, very small. So even in case, smaller than any inverse polynomial. Okay, so that's kind of all I'm going to say about the analysis, but really this intuition of, breaking up the sum based on whether or not you had a good first stage is actually very crucial to the analysis. Okay, but what's kind of unsatisfactory about this is that, okay, up till now, I've only been focusing on F2. And if you recall, we really needed a large field, right? Because my soundness error was something like 1 over the size of the field, or in fact, 1 over epsilon times the size of the field. Yeah, anyways. So probably in practice, F should be like a size like 2 to the 128 or some massive value like that. Okay, what's the trivial way I can get a code over a large field if I have a binary code? I just use the same generator matrix, right? I mean, if I have a matrix of 0 and 1s, I can still apply it, to messages where the coordinates now come from, say, an extension of F2. Okay, I mean, the thing is, of course, the rate stays the same because that's just a property of the matrix G having full rank. And also you can check the distance won't get any worse, but that's kind of unsatisfactory. So you might ask, can we do better? Right now we're getting rate 1/4 and distance 0.19, which is great if you want a binary code. But if I'm allowing you to use a massive field, you could hope to hit something like the singleton bound, rate 1/4 and say distance 3/4 then, right? So I'm quite far from that. So let me just I have pretty much my last slide until I state some open problems. How could you imagine sort of working over a large alphabet? Let's say I have like a fixed vector of a given weight. What I kind of care about is transforming it into a uniformly random vector of the same weight, right? Because that was kind of the important property of the permutation that we used when we were analyzing the RA code. So here we again still have to sort of randomly permute the coordinates of x, but actually you also need to sort of rescale, right? So I'm just kind of rephrasing the fact that like, what are sort of the isometries of like, this Hamming space. It's, I'm allowed to permute coordinates and also rescale things. Okay. And a reasonable way to define an RA code over an extension field to be in this form. So this is again my notation for the repetition matrix. So I first repeat everything 4 times, and then I do this permute and then this random diagonal matrix, and then I just use the same accumulator matrix. And I would conjecture that these codes have great distance. I might even be bold enough to say like singleton bound if you make Q large enough. But we don't know how to analyze them. And actually, there's a very subtle, very important challenge here. It's actually because the expectation, before I just said use Markov's inequality and you're happy, you just say you can prove the expectation is small. But here it's actually provably not true. Like the expectation is large. So you need sort of a more careful analysis beyond just Markov's inequality. I have some ideas here, but this is still sort of ongoing work. Okay, so this brings me then to the open problems. So first of all, can you analyze these codes directly over larger alphabets? And in fact, there's already been some previous work on sort of a related question. I will say that this work, it's actually quite interesting what they do, but what they sort of managed to do is say that large fields don't hurt you, which is, okay, it's actually non-trivial even to prove that. But I'd like to say that large fields actually help you. You should actually be able to get better distance, not just that the distance isn't getting worse. Now, this is sort of where I make a tenuous connection maybe to high-dimensional expanders, but it'd be very nice to have explicit constructions. Right, so I said, we're randomly sampling these permutations right now, and it's not even clear to me what sort of the right pseudo-randomness property that you would want for these permutations to be in order to guarantee good distance. There was one work by Venkats and I can't recall the first name of this other author, but they basically showed how you could, there was a way to choose the first permutation, and then over the randomness of the second permutation, you would have good distance, so it's sort of a partial de-randomization. Actually, even for a cryptographic perspective, something which would be very interesting is if you could do something where you sample your RAA code, and then even if the permutations are sampled randomly, you can somehow show that you do some additional tests, and then conditioned on these tests passing, you'll say the probability that the code has bad distance is now negligible in n. We already do something like that where we can say maybe the failure probability, if it was originally 1 over n, after you run these tests and conditioned on the test passing, you might have failure probability 1 over n to the 4. So you can get smaller and smaller polynomial failure probability, but never anything that's more than inverse polynomial or smaller than inverse polynomial. Okay, so then also sort of touching on what Shubhangi was mentioning. So could we have improved proximity gaps? And also maybe could tailor-make them for RAA codes. I don't know if they really have enough structure to work with. They're not nearly as nice algebraic codes like Reed-Solomon codes, but maybe there's something to be done there. Now I'll say something which is maybe a bit controversial. So a natural thing you might ask about any code, of course, is can you decode them? But actually, from a cryptographics perspective, we'd actually sort of hope that you can't decode them. Because in fact, in some prior works I've been a part of, we use these codes as kind of a component in a different cryptographic construction. And one of the requirements for security is that you can't decode these things. So, okay, it would be interesting to see if you can decode them, because then, of course, we would have to revise these papers, but that would also be a lot of work for me. So maybe I'm hoping you fail. But anyways, that's all I have to share. Thank you. Yeah, so, okay. First of all, it was important that the codes have rate, which is, for the specific application, it needs to be 1 over a power of 2. So that kind of, so you could hope for maybe 1 over 2. That would be sort of the optimal thing. But actually, then you need at least 3 rounds of accumulation to get good distance, it seems. And then the analysis got very messy, and okay, 1/4 was already pretty good. But yeah, in principle, if you wanted rate 1/2, you would do 3 rounds of accumulation. So that should work. You could also do any rate 1/3 as well, but yeah, for our context, we needed it to be a power of 2. So. In what sense? Like you're saying, oh, you're saying instead of just repeating or something, I have a smarter, yeah. So there are, Okay, so to do that, you would need to have a very good understanding, at least if you want to use kind of this sort of analysis of the expectation, I would need to have a very good understanding of the weight distribution of the initial code, right? So that's kind of what I'm using. I'm sort of using the trivial fact that like if you were to do this repeat 4 times, I know it's weight distribution. But yeah, in principle, if you had a very good understanding of that, you could maybe use it, yeah.
Thank Nick again. We now break until 5 p.m. Yeah.